Swayam Prabha. Digital India. Educated India.
Hello, good morning. So, welcome to the course on comprehensive view of speech processing, and today's lecture is 38 in series, and today we are going to discuss another important the speech task. It is the speaker recognition, and and yesterday in last two lectures we discussed about the two speech tasks, a very well known speech task known to be speech coding and then automatic speech recognition. So, these are the two tasks we discussed prior to this, and today we are going to discuss about speaker recognition. And before going to the details or the discussion on speaker recognition, I just want to spend 5 minutes to conclude the yesterday's lecture, that is automatic speech recognition. And here in the last lecture we are discussing about a template matching. So, this is basically, suppose you perform, when you are trying to perform the isolated word recognition task, isolated word, the speech recognition, one of the task is like isolated word recognition, connected word recognition, and other one is the continuous speech recognition. In case of isolated word recognition, the task is to given a speech signal and you need to find out what is the word that speech signal carries. It's basically here the task is that we are expected that only the speech signal carries only one word, and we need to determine what that word is. It's nothing but we need to determine the text form of that. So, for that, since it is only one word that is present, so therefore here for validation of that or for testing that one, you can use the template matching, and for that we will prepare some reference template. Reference template means we will take some samples of the word uttered by the different people or different humans, and then we will extract the feature vectors and we will try to take the mean of all those samples, and that can be treated as a reference template. And afterwards, when you are testing the case at the time of testing, so if you utter the speech word, if you utter the speech signal, and from that we will try to extract the feature vectors after you detect the boundaries, and those feature vectors will try to match with the reference template. So, that way, for example, if your task is that like a digit recognition task where you have only 10 words are possible, right. So, in that means that there are 10 word templates used to be there, and we need to check that from a given speech sample we will extract the feature vectors and we will try to match this sequence of feature vectors with the 10 word templates, like these templates corresponds to 0, 1 to up to 9. So, whichever the word template gives you the best score, or you can say the least distance, then we can hypothesize that the given speech signal carries the particular digit. And for doing that, here the issue here is that in case of template matching, the issue here is that the length of the word, the duration of the word may not match with the reference template, because in the reference template the word from the word when you extract you may have 20 feature vectors, but when you are testing the new word where it may contains either 22 vectors or it may have 17 vectors, because the speech is like we have some inherent variability will be there. So, we cannot expect the duration of the word will be exactly the same as the reference template. So, here how do you do the time alignment and all? So, that we can able to carry out by using a technique known to be like a dynamic time warping. And here the idea of dynamic time warping is that, suppose for example, this is your reference template which contains about like there are n feature vectors, we will concatenate all of them. So, these are the n feature vectors corresponds to the reference template, and in your test case the number of feature vectors will be m. Number of feature vectors will be m, and where this n and m are not equal. So, in that case how do you match? How do we match the feature vectors? The way here is that we will perform the dynamic time warping. The idea here is that, so we will take a reference the test feature vector, we will see that the first feature vector, and the first feature vector is matched to like there will be like the window will be considered, the window length will be like suppose W, it may contains like 3 vectors. So it means that the first feature vector from the test utterance is compared with the first 3 vectors of the reference template, out of which, for example, the second vector is giving the least distance, then we will mark this as the second vector is a matching to the first vector, and so then we will join that, and afterwards we will take the second vector from the test template, and then since already now the second vector of the reference template is matched to the first one, now for checking the distance from the second frame of the second vector of the test template, now we have to consider from the second vector to like another 3, like a second, third and fourth of the reference template feature vectors are considered, and here from this we will try to find out which gives the least distance. So here in this case, assuming that for the second feature vector from the test word, it is matching with the like the second word, it's the second feature vector itself. So that way we will mark it. So that way we will keep on checking the test feature vector with the reference feature vectors, starting from like from the preceding the match, whatever is the like the feature vector whichever is matched from the reference template, from that we will consider the window length, from that the window will be started. So that way each time we will try to find out the match against the test vector to the reference 3 reference vectors, out of that whichever gives the minimum match we will mark that. So that way, so the matching path can be established between the test vector versus the reference vector. So that way we will try to compute the the distance between the test feature vector, the test word or the test word sample that is considered for the testing case to the reference template and all. So that way, so here here the thing is that the number of feature vectors in the test utterance is different from the number of feature vectors from in the reference vector. In that case, how do we match? How do you find out the distance and all? So this way you can use the time warping method, dynamic time warping method, we can able to consider that. So here actually in principle the window length should be like a total complete, like, but no that is very expensive, because if that is the case, the number of comparisons that are required will be n times m, right. For every word sample, if you want to test, you have like nm computations are required, but in principle, since the intuitive way, if you look at here the feature vectors, since both of them are from the like they are at the word level, so therefore we expect that if the reference template and the test case both are same, then the match will be like a first within a range. So therefore we will consider the window length of either 3 or 4 vectors, and within that we will try to find out the match. So that way we will establish a path, is known to be warping path, and with this warping path we will try to find out the distance between the test feature vectors to the reference feature vectors, and that is the way we will find out the distance. And suppose in case of digit recognition system, we have like a 10 templates used to be there, corresponds to each of the with respect to each of the digit, like 0, 1, 2 up to 9. And from the test case, whatever the word that is spoken, so we do not know, we need to hypothesize, we need to determine that. So therefore what the feature vectors extracted from the test utterance are compared with the 10 reference templates associated to the digits, and whichever the reference template is giving the least match, is giving the least distance or like a highest score, so that particular digit is hypothesized as the word label. So that way, using a dynamic time warping, you can able to like perform the classification. It's nothing but performing the match with the reference templates, and then based on the classification problem, based on the classification decision, we can able to hypothesize, or we can able to label the given word. And then coming to the development of ASR systems, usually the ASR systems, whatever we have discussed so far, the framework which you mentioned in the very initial, at the beginning also, they are basically consists of acoustic models followed by language models. So prior to the acoustic model, we have feature extraction module used to be there, and from that the sequence of feature vectors will be extracted. Then using acoustic model, we will transform those feature vectors to like the sequence of symbols or sequence of sound units. And from the sequence of sound units, by applying a language model, we can able to derive the sequence of words. So this is a general phenomena or conventional way of performing the ASR, having the 3 or 4 modules in a sequence, and the initial module will take the input as a speech signal, and the last module will provide the output as sequence of words or the text. So, this is the conventional way of performing ASR, and now recently due to the like a proliferation of like large computational capacity and storage capabilities and all. So, the deep architectures have been evolved, and using these deep architectures we can able to perform this ASR in an end to end manner. It means without considering these the modules, the internal modules like feature extraction, then followed by acoustic model, then followed by language model, consists of different stages. Instead of considering the different individual modules, we just integrate all of them, put together as a single module, and then input as the speech signal, and output will be the sequence of words or the text. So, that way these end to end models have been evolved using the DNNs, deep neural networks of different types, like LSTM, like is known to be like long short term memories, and by LSTM there is a bidirectional long short memory, CNN, and so on, like transformers and so on. So, by using these various architectures you can able to perform the end to end models, and the one advantage of this end to end model is that actually, since we treat all of them put together, and then we will try to optimize the whole module, the parameters or the control parameters that are involved in the whole system have been done from input to the output in one goal. Whereas here we have individual modules are there, so trying to optimize each module may not be optimal for other modules. So, that way it will be parameter optimization will be difficult or very complex in case of conventional ASR systems, whereas in case of end to end models we are not considering the individual modules, we are just taking the input and output through a complex system, and the parameters of the complex system will try to like optimize with respect to a huge amount of data. So, but here the requirement is that in case of end to end model, huge amount of data is required, labeled annotated data is required. So, if it is available, then it is better to go for end to end models, where the performance of the models or performance of the system is very high and robust also. And coming to the generic issues in developing the acoustic model, that we have seen the choice of symbol. That means, if you use the conventional model, we have one of the module is acoustic model, where it used to transform the feature vectors to the sequence of symbols or the sequence of sound units. And here the thing is that what is the which sound unit or which of the symbols can be considered, whether phonemes or syllables, words or phrases. As you see, phonemes are the units which are very limited in number, 40 to 50. So, therefore, from you can able to build the system, building the systems will be easier using the phonemes as units, but the problem is that phonemes are highly variable, and getting the label data and even detecting these phonemes in the speech signal also very difficult. And then coming to the other units like phrases and words, the numbers are very huge. We cannot build the models for every word or for every phrase, since the numbers are like in terms of millions and crores. So, we cannot practically we cannot build the models at word level or phrase level. So, the intermediate one is somewhat syllables, where you have, in case of syllable, it is nothing but it is a multiple phonemes, where the vowel has to be there, vowel is must, and the consonants may or may not associate with that. So, most of the Indian languages are syllabic in nature. So, as you have seen that most of our languages are like the vowel is present and then consonant may or may not present. So, it is known to be graphieme, it is equivalent to the syllable. So, that way we have the order of these number of syllables will be around thousands, and but here the characteristics are somewhat stable compared to the phonemes. So, that way they are depending upon the thing we can able to use either syllables as the phonemes as the right units. Then coming to the feature extraction, there are standard ways we have already discussed using linear prediction analysis and the different types of the feature extraction techniques, using CAPSTRUM analysis, spectral analysis, linear prediction analysis, and auditory analysis. So, there are different ways you can able to extract the features, and also instead of using signal processing methods, using a deep architectures also can able to derive the features using autoencoder based features. That means, using a deep architectures, you can by having encoder and decoder combination, you can extract the features from the intermediate layers and all, and with that the features will be like they represent the actual hidden relations that are present in the data. And along with that, the other issue are like in the conventional models, detection of syllable boundaries is also very tough. As I mentioned, in case of phonemes, if you want to detect the boundaries of phonemes, it is very difficult because it is highly variable and it basically depends upon the context. Sometimes you can able to perceive the specific phoneme, but when you try to find out its location in the speech signal, it is very difficult to do that. So these are the various issues that are involved when you are developing the ASR systems. And coming to the applications of ASR systems, as we have seen already, we come across in the as part of a course at different occasions. We have seen voice. One of the very important applications is the voice interface to machines. It's like in case of robotics or in case of industry and all. So we can having the other interfaces like switches and other things we can overcome by using a voice interface. And speech to speech translation is very much useful for in the context of multilingual countries, particularly in the context of India, where we have several languages. So just if you cross about if you just go around 400-500 kilometers, you can find some other language where the people used to speak. If you want to have a dialogue in a very seamless way and flexible way across the country, from across the states, it's better to have a speech to speech translation. So in that speech to speech translation, one of the module or one of the in the framework, overall framework, one of the module is ASR and all. So first you will perform the ASR, you can derive the text, and then from that text, depending upon the target user, you can able to translate the text into the target language, then you can able to synthesize that. So that way speech from any language to any language you can able to convert, like a speech from Hindi to convert to Tamil, and Tamil to the Malayalam. So likewise you can able to perform. So in that, one of the module that is required will be the ASR system. Automatic dictation systems, as we are seeing, this is a personalized one. And then personalized applications in case of when you want to interact with the home appliances or mobile phones, etc. You can have the personalized applications where the personalized ASR are very much useful. Automatic form filling applications. So this is very important applications we come across in the recent times, where we're trying to fill up various forms where we used to use the keyboard to type the different fields. Instead, it will be nice if you have automatic form filling with a voice interface and all, right. So if you have interactive, then in that case it will ask for a different specific field. Instead of typing that, you can able to utter that directly, so that it will be the corresponding text will be generated using ASR, and that will be filled up automatically. And indexing, retrieval of speech documents, and social data analysis, because in the social data platforms we have different ways like a Twitter, Facebook, WhatsApp and so on. So all these things contains the different the speech documents or audio information recordings used to be there. So if you want to analyze that them in a different perspectives, you can use the ASR is the first one, where it can be converted to text and you can able to analyze the text. And similarly, healthcare applications also, and speech coding, speech compression, speech transmission, all these cases also we can use ASR, where you can convert the speech to the text, where with very low data rates you can able to represent the corresponding. Otherwise, the normal speech, if you want to do with the PCM coding, it requires about 128 kbps or 256 kbps, whereas once if you convert that speech to the text, the number of bits that are required to represent the same speech utterance will be very less. But it may not contains the whole information that as the actual speech signal contains, but it contains the message, and depending upon the task you can able to use the ASR for speech coding, compression and transmission. So there are so many other applications, but here just few of them are listed over here and all. So with this we can conclude the ASR is one of the speech tasks used to build the speech recognition system. And now if we move on to the regular topic of this particular of today, it's speaker recognition. And here, as I mentioned, in case of speech recognition, our objective is to, from a speech signal, you need to derive the text or a sequence of words. That was the objective of the ASR. Whereas in case of speaker recognition task, the objective is that given a speech signal and we need to perform, or the system has to indicate that who has spoken this utterance, or nothing but providing the speaker identity. That was the task of speaker recognition. We do not bother about like what the speech signal contains, what the message part is not interested over here. Here the thing that need to be performed will be who has spoken that, right. So, the speaker identity has to be revealed from the speech signal. That was the task of speaker recognition. And coming to the personal identity characteristics, we have various modalities where we have a facial features, or the face can be used as for speaker identification or like person identification. Voice is one of them, fingerprints, iris, DNA structure. So, these are the various traits or various modes where you can able to perform a person authentication, right. And one of them is the voice, right. And coming to the voice based person authentication, the applications are based on this, like basically for a security point of view, surveillance and forensic applications and all. Coming to the voice as a biometric, the advantages are that because you can able to collect this speech sample as a voice very non-invasive way, and very low cost transducers can be used to capture the speech data, right. And without even the cooperation of the speaker is also not very much required. Whatever the speaker speaks from a distant microphone, you can able to capture the speech signal and you can able to validate who has spoken that. So, that way, that is a non-invasive way you can able to do that, and it is a convenient way of capturing the speech data using simple transducers. And another thing is that it is useful for remote access. That means by using telephone networks. So, if you can able to access, suppose if you want to perform any banking application and all. So, using a voice interface you can able to carry out that. So, with that it can be used as a authenticity for authentication purpose. You can use the voice, and where the voice can be transmitted through a telephone networks, that can be possible. If that means in a distance mode or from over a distance, if you want to access any transactions which are related to security. So, that you can, in that case you can use the voice as a biometric. And the drawbacks of this is that and the main drawback is that particularly the speech where it is subjected to variability, source of variability. It means that involuntary, like it means that as we have known that the speech signal contains some inherent variability. So, with that we cannot repeat the utterance in the same way. Suppose we uttered some word, and if you try to utter the word in the second time, so these two words whichever have the same words even though uttered, but they are different. If you look at the time domain signals, they are different. That is what involuntarily, that means it is it happens. So, it is inability to repeat the utterance in the same way, it is one difficulty. And the other one is the voluntarily, like the speaker wantedly also can able to change the way he speaks. So, that is all. With that actually can able to disguise the other's voice also. He can mimic the other voice, so that he can do he can do the spoofing, those activities also can be carried out. So, those are the drawbacks that are associated to the voice as a biometric. And along with that, when you are using a voice or the speech as a like for recognition purpose, speaker recognition purpose, there are the background environments that also will be captured along with the speech, that depending upon where you are giving a speech sample, background noise, transmission channels, and the recording microphone added noise. So, all these things also will be added. So, with that also it will be there is a difficulty in like recognizing the speaker and all, because the speaker model that is built with some other environment, and when you are testing, if you are recording a speech in a different environment, then the mismatch will occur, and with that the recognition task may not be carried out. And the basic approach for speaker recognition will be, this is the one, this is a standard one, like a speech and pre-processing. It means that if there is any noise or something, we can filter out the noise and will extract the features. This block is similar to the one what is used for speech recognition also, and then use the extracted features for building the speaker model. So, here here the feature extraction, the similar module we have used for speech recognition also, but here the modeling task will be, in case of speech recognition, the models that are performed are built with respect to the sound units, right, whereas here the models are built with respect to the speaker. So here the thing is that here the features whatever we are extracted, so the extracted features should highlight the speaker specific information beyond the sounds, beyond the message what was spoken. Whereas in case of speech recognition, we will try to see that the features will try to highlight the sound unit, the sound specific information compared to the speaker specific information. And you can use here the speaker models can be built with the either GMM models or neural network models, like. So, any of the models that we have discussed, even HMMs can be used. So, those things can be used for building the speaker model. And once the models are built in the training phase, then those models can be used for testing purpose or evaluation purpose, right. So, here use the similarity measure, and based on that we can able to identify who has spoken that. And here the last block, the decision with the threshold. So, this is used for speaker verification task. In a speaker recognition, there are two different tasks. One is the speaker verification and other one the speaker identification. We will see the difference between those two. The speaker identification is that in case of speaker identification, and so it means that actually from the given speech sample, we need to identify who has spoken that among the available speakers. Suppose we need to identify the speaker identity among the 50 speakers, then we have a 50 speaker models, and the features that are extracted from a test utterance will be validated with respect to all 50 models, and then based on the maximum probable score we will decide, or we will make a decision that who is the speaker identity. Whereas the other task not to be speaker verification, where in that, so along with the speech sample, so we need to verify that whether the speech sample belongs to a particular speaker X. So, in that case here we need not compare the features with respect to all speaker models. Whoever is the speaker identity has to be verified, only with respect to that particular speaker model we need to match, and whatever the similarity score that was there, so that will be tested with respect to threshold. So, if this score is greater than the threshold, then you can say that yes, the speech that is uttered by the speaker X. Suppose if it is less than the threshold, then we say that no, the speech utterance whatever is given is not belongs to the speaker X. This is not to be speaker verification task and all. So, example, this is similar to the one, for example, in case of banking, when you are performing any transaction in a conventional mode, we will sign at the end of a check or so, right, at the bottom of a check. So, there the bank employee, he will check the signature whatever you have made it, and the check with respect to the signature that you have given during the account opening time and all. So, it is a kind of verification, verifying the signature and all. Similar to that here also in case of speaker verification. So, the voice sample whatever is you are giving, that you are verifying with the specific speaker, and then with that you are validating that whether the speech utterance that provided belongs to the given speaker or not. And so, this is the probabilistic approach of speaker recognition. So, this is just similar to the one what we discussed in case of speech recognition. So, here you can see it is argmax of, there are various speaker models, now so many speaker models. So, SI where I belongs to, I may be varying from 1 to 50 in case of 50 speakers, right. So, we will and O is the observation sequence, nothing but the feature vectors. So, from a given set of feature vectors, we need to compute these speech vectors belongs to which of the speaker. So, we will try to find out the posterior probability of the speaker given the observation sequence, and among the 50 speakers or whatever the number of speakers, whichever speaker model gives the highest score, highest probability score, that will be hypothesized. S star is nothing but the speaker identity, that is the maximum among the set of speakers. And here from the observation sequence, we can extract the features from different components, like the speech we already studied, we already come across speech can be derived, can be viewed as exciting the vocal tract system with the time varying excitation. So, that way the speech signal, from that you can able to extract the excitation source features and then the vocal tract filter features, And from the speech, if you analyze the longer speech segment, that is a suprasegmental level, we can get some other information at higher level, right. For example, the way the intonation of the speaker and the way the duration patterns of the speaker, right, all these things will be by analyzing the longer speech segment. So, that way from the observation sequence one can able to analyze the speaker identity with respect to the different components or different types of information. Excitation source R is nothing but residual or excitation component of a speech, and F is nothing but the vocal tract filter component of a speech, and X is nothing but suprasegmental information related. So, with respect to these three, one can able to like compute the posterior probability of a speaker, and that you can able to do it by using this formulation, joint probability of all of them with respect to this, and this is in turn can be done by using a conditional probabilities, right, like the speaker identity with respect to residual, speaker identity with respect to this one, that way you can able to do it, right. And from this all of them, and so this way you can do it, and from this you can see that here the denominator is common across all the speaker identities, right. And similarly the PSI is also the posterior the prior probability. Suppose if we have no idea about the prior probability of the speaker, then you can also ignore this one, then the leftover will be only these three factors, right. And so that way you can able to compute like compute the speaker identity based on this, taking the product of the posterior the probabilities that are associated to with each of the features. And since assuming that there are k features, right, the set of features consists of k, for example, then each of the feature vectors are independent, then you can compute by taking the probabilities with respect to each feature vector and multiplying them, and then if you take a logarithm over that, so then this multiplication becomes the summation. You can see this is the product. If you take a logarithmic of that one log likelihood, then this becomes the summation. So that way you can able to compute the you can able to validate you can able to perform the speaker recognition in the probabilistic framework, right. So, and here the definitions, as I mentioned, that speaker identification is nothing but from a closed set of speakers we need to identify who has spoken the utterance. In the open set, right, so you need to, sometimes the speech utterance may not belongs to the given closed set. So, in that case we need to validate, we have to tell that the speech that is uttered by the speaker is not present in the group of speakers. So, here when you are discussing about different types of speaker recognition tasks, that means in the speaker recognition there are basically two tasks, as I mentioned, speaker identification and speaker verification. And speaker identification is nothing but, so from the given speech utterance you need to find out who has spoken that from a given set of speakers, and this the set it may be like a closed set and open set problem. Closed set means the assumption is that the speech utterance should be from the one of the speakers in the group. The open set may be the speech utterance may be from the group or it may not be. So, that is the open set identification. Speaker verification, as I already mentioned, is nothing but verifying the identity claim. So, in that case, no, we need not verify with respect to all the speaker models. Whatever the claim has to be verified, only with respect to that particular speaker we will validate, and then we will take a binary decision whether it is yes or no. And then the speaker detection is nothing but, it is nothing but here in case of, suppose for example, in a case of the meeting environments where there are several speakers or several people are present in a meeting hall, and people used to speak like one after another in a systematic way. So, then finally, when the speech that is collected through microphone, it contains the multi-speaker speech. So, in that case, so we had to decide, we had to detect the speakers, the speaker turns, right, who has spoken when. So, that way from the speech signal, first of all we need to track the speaker, that the speaker 1 may present in the first 5 seconds, then afterwards the speaker 2, 3 and 4 might be spoken, then again the speaker 1 turn may come, speaker 1 may be spoken. So, in that case the task is not to be speaker detection, that means in the multi-speaker speech, so detecting a particular speaker when he has uttered during, suppose for example you have 10 minutes of speech. So, the speaker 1 at what time instances the speaker 1 has spoken, right. So, that way that task will be where there also it is a speaker recognition or speaker detection task, but we need to find out like various speakers who has spoken when, like a speaker tracking, speaker segmentation, speaker indexing, speaker diarization, all these things is a part of that particular task. And again in the speaker recognition, the task will be either text dependent and text independent, right, either text dependent or text independent case. So, text dependent means for a particular systems where you need, it's a kind of a password testing, like you have to use the same password for authentication. So, in that case here instead of normal password, it is like the same speech utterance has to be spoken, and against to that it will be validated. Whereas in speaker text independent, there is no constraint on the specific text to be spoken. And so, in the case of speaker recognition, there are like the features may be the speaker specific features may be the physiological or at higher level. Like physiological means the way because the speech is produced by the vocal tract, and also that way the shape of the vocal tract, the movement of articulators, the spectral envelope, formants, all these things are related to the physiological characteristics are related to the speaker, because they are related to the speech production mechanism. And higher level speaking behavior means the choice of words. Then when the speaker is speaking, the kind of words that he is using and the kind of syntax he is using, the way he is varying the pitch, intonation patterns, rhythmic patterns, and the breathiness. So, all these characteristics are corresponds to the behavioral characteristics and all. So, these are the higher level the features, whereas these are not to be the low level features are the physiological aspects of a speaker recognition or aspects of a speaker features. And again the features may be either segmental or suprasegmental. So, the segmental means actually here by analyzing the smaller segments of speech, that is mostly attributed to at a sound unit level. Suprasegmental means it is a sequence of sounds, it is a word level or a sequence of words at phrase level. So, those at those levels, what are the speaker specific characteristics that are present that can be exploited for speaker recognition. So, as I mentioned already, the low level features and high level features, whichever I have already mentioned. So, usually the low level features means they are related to associated with the periphery of the brain perception of the speech. That means in the brain there are specific areas where that are related to the speech perception, and here the low level features are basically used to the periphery of those the regions and all, whereas high level features are basically the core or the central points of those things. So, that is the reason that actually humans can able to effortlessly perform various speech tasks, and whereas the machines and all we are using the low level features. So, that way it will be there is a difficulty in performing the various speech tasks, either it may be speech recognition, speaker recognition, language recognition, and so on. And then coming to the applications here, there are several applications here, just I have listed some of them. You can go through that. It is very obvious and intuitive. You can able to security, forensic, surveillance, indexing the multimedia, because there are multi speakers are involved, right, and improving the speech recognition, as I mentioned, because the speech is uttered by the different speakers where the speaker specific characteristics used to be there. So, if you want to improve the speech recognition, so if you build the speaker specific models, then the performance of speech recognition also will be improved. And the speaker features, as I have mentioned already, the low level and high level features, as I already mentioned. Low level features means basically they are like related to the speech production mechanism or the vocal tract shape and formats and so on, whereas high level features means the usage of words and the sequence of phones that are used, how they are uttered. So, those are the high level features and all. Then coming to the based on the applications, the speaker models will be built. As I mentioned, like sometimes you can use the speaker recognition models based on the text dependent, like using the password based. So, in that case, since it is just password, so therefore, here the temporal characteristics of the speech specific to a speaker are analyzed, whereas in the other cases where the pervasive surveillance applications, where we use the more detailed the features, like for example, the usage of words and entire acoustic space, the features that are the background, everything will be considered for analysis purpose. And for building the speaker models, as we have seen, there are like non-parametric and parametric approaches. So, non-parametric approaches we have seen, like DTW is one of them, like the template matching, and other one is the nearest neighbor. So, using this we can able to carry out the speaker verification or recognition using this. And coming to parametric approaches, there are many, like you can have vector quantization, GMM, HMMs, right, and support vector machines, and even other approaches, even the hybrid modes, hybrid approaches. That means there is a multiples of these combination of these approaches can be used for building the speaker models and all, right. Then the speaker adaptation. So, here the adaptation means, here when you are building a speaker models, there will be a mismatch between the training phase and testing phase, right. So, that means the speech may be arrived from, for example, various testing conditions. Maybe when you are building a speaker model, you might be considered, or you might have collected the speech in a clean environment, in an indoor environment, but when you are testing that, the same speaker has recorded the speech, or the speech was uttered in the outdoor or in a very crowded place. So, in that case, the testing features or the speech features that are extracted during the test utterance are very different from training. So, in that case, we need to have a speech speaker recognition in a robust way. So, the adaptation is required. So, the enrollment and test conditions, they will be varied. So, therefore, we need to have proper adaptation is required, because there are various channels, different channels and different recording devices, and different background noises, different linguistic contents. So, all these scenarios where we expect to have proper speaker adaptation is required, so that the speaker recognition system will be robust enough. And again, there are adaptations at a model level adaptation and the threshold adaptation, that depending upon the environment where the thresholds can be varied. And here the decision, how to, while performing speaker recognition, the decision mechanism we have seen already. This is the same probabilistic approach in the case of speaker recognition in a closed set environment. And in case of verification, so where only the specific model against to that has to be verified. That means, here we have to check the speaker, the probability of this one, it is not as the probability of this one for a particular speaker, whether that is greater than the threshold or not, right. So, that way we can able to perform that. Similarly, in the case of open set identification is nothing but both the closed set identification plus verification. That means, closed set identification will do that. If none of the speakers are matched, then we will just check with the this one with the verification task also. And then when you are performing the speaker recognition task, when you are setting the threshold should be set by using this formulation. Here the CFA and CFR, they are corresponds to the desired false acceptance and rejection rates. Here false acceptance means, right, for example, when you are verifying with respect to a particular speaker, suppose or when you are recognizing with respect to a particular speaker model, even though for a false cases, that means imposters will be accepted as a genuine speaker, right. So, that is not to be false acceptance, that should not be, because you have to minimize that. Similarly, false rejection, that means when you are testing with respect to a particular speaker, the speaker model is a genuine model, that means the particular speech utterance corresponds to that particular model, but you are rejecting that. It means that the genuine cases are rejecting. So, it is not to be false rejection. So, both should be lower, that means the genuine cases should not be rejected and the false alarms should not be accepted. So, both should be lower, right. So, therefore, the desired it means these are the desired rates of false acceptance and false rejection. And the PIMP is nothing but the prior probability of an imposter, So, using this formulation you can able to set the threshold. And the score normalization, when you are deriving the scores or the probabilities, so we need to take care about the various normalizations we have to carry out. It means T norm means actually like a transmission channel normalization, H norm means handset normalization, Z norm means zero normalization. So, that way, like since as I have seen earlier in the previous slide, so where there is various scenarios where you need to perform a speaker recognition, right, in the different background environments and the different channels, the signal will be captured, and the different handsets, different microphones. So, there are various scenarios. So, when you perform a speaker recognition to get a speaker recognition task in a very robust way. So, we need to perform this normalization so that the speaker recognition performance will be more accurate. Yeah, the same thing I have mentioned. When you are evaluating the performance of a speaker, these are various performance techniques that evaluation techniques will be used. One is the like a probability of detection, nothing but 1 minus PFR, it is a false rejection. So, here is the case out of detection, how many of them are the true ones or be rejected. So, 1 minus of that gives you the probability of detection, like it is nothing but the true positives, like how many were detected, right. So, in that case actually here if all of them were properly detected, it becomes 1 because this is the missing will be 0. So, it will be 1, and there are other characteristics, other ways also can able to evaluate the speaker recognition, to be receiver operating ROC, detection error trade off, and equal error rate. So, there are different ways you can able to analyze the speaker recognition performance, and when you are performing a speaker verification task, the cost function that need to be optimized will be based on this. Like as I mentioned, like the CFA and CFR, the both should be minimized, right. CFA means false acceptance, CFR means genuine rejection. So, both should be minimized, right. And so, when you are performing a cast, you need to like take care about by using this, you can able to the cost function can be minimized. And here receiver operating characteristic means this is actually derived from the telephonic receivers, like not telephonic, like in a standard detection theory, where the ROC characteristics will be used for analyzing the receiver performance and all. So, here also the similar thing have been used adopted. So, therefore, the ROC characteristics also can be used for speaker recognition performance. And equal error rate means actually here we will try to fix the threshold such a way that both these like errors like false acceptance and false rejections are equal. Here you can see this is a plot known to be DET plot, like a detection error threshold, like here you can see here we are plotting here we are fixing a threshold or we are varying a threshold, and by at each threshold we will try to plot the probability of miss versus the false alarm. It is nothing but a false acceptance versus the false rejection. So, when you are keeping a threshold at this point where you have maximum miss probability and the false acceptance is 0, almost very null, and then as you vary the threshold where the false acceptance is increased and the miss probability will be decreased, and when you come to this extreme where the false acceptance is very high and the miss probability is the lowest. But if you want to have like the equal error rate is nothing but we need to have a threshold where both the miss probability and the false acceptance will be the minimum or equal. So, in that case if you draw a line here, the 45-degree line, wherever it crosses it indicates the corresponding threshold where the false acceptance and false rejection both are same, right. So, here you can see these two plots are nothing but if you perform a speaker recognition task or speaker verification task using a Gaussian mixture models with the different types of with the different components, number of components. Suppose if you use the 512 Gaussian components, the DET plot will be this one, the blue one, right. And if you use the more number of Gaussians, 4 times to that, like 2048 Gaussians, if you plot the DET plot, if you vary the threshold, then the red colored one seems to be the DET plot corresponds to 2048, right. And here you can see that using the blue colored one, the equal error rate is appears to be like 9%, whereas with the red colored one, if you see the like detection error threshold, the equal error rate is 8.5%. 8.5%. It means that there are 8.5% of false alarms and 8.5% of like a false rejections also. So, this way you can able to evaluate the speaker recognition performance using equal error rate by plotting the like a DET plot. This is a decision error threshold, because there is a threshold, the threshold has to be varied, right, and the threshold will be fixed such a way that both the errors are equal. And the selected applications of automatic speaker recognition, one of them is that indexing the multi-speaker data. We have seen that. How do we do that? Here just very briefly the steps were given, because assuming the data is a multi-speaker data, first of all we have to identify the boundaries of the speakers, right, in the multi-speaker speech. Then afterwards you need to perform the clustering with respect to the speakers. Then afterwards use those modus clustered data, and again we have to refine that. So that way at the end, after iteration, you can come to know that actually each speaker at each cluster the speech corresponds to a particular speaker will be clustered in each node and all. And then the forensic applications and the customization. Customization means, as we have seen that in case of speech recognition applications, if you customize the recognition system, for example, if you have automobile system, suppose you are automatic driving car, for example, where all the controls you can able to control by using voice interface. And since the car is your personal your thing, it's better to like customize to mostly like for your case, so that if others want to use that in a voice interface, it should not work. Like there is other alternative, you can use that without speaking mode, you can able to carry out the task. But if you want to do that, so for customization of that one, like email reading to a particular user, right. So this is an application where you can use the speaker specific characteristics. So with that you try to build a model where that you can use that. Similarly, caller identification, all these things you can try to customize to your personal environment, and you can perform that. And similarly, as I mentioned, like you can use for performing speaker recognition, you can use the various features like excitation source features, vocal tract features. Prosody means it's like the features that are extracted from a longer segment or a supra-segmental nature. So these features are basically intonation, duration patterns, loudness, stress, and so on. And similarly, ideolect features, nothing but behavioral features like the type of words that are using, type of phrase that are using. So these are the various features that can be used for performing the task. And the same thing at different levels, you can able to extract these features like subsegmental, segmental. Excitation source features can be extracted from subsegmental level features, and segmental level features are basically for capturing the vocal tract characteristics. Suprasegmental features are used for capturing the prosodic features, and similarly ideolect features are used for capturing the like at a very higher level, like kind of phrases the speaker is using, kind of words the speaker is using. So in that context, the ideolect features can be used. And if you look at the prosody, speaker specific prosodic aspects of prosody, what it means is that, so if you visualize the prosodic features, how for a different speakers, how the prosodic distribution or the prosodic features are different. Here if you look at A and B, they are the F0 distributions of the two female speakers. You can see here, here the distribution, the range may be same, but if you look at the mean are different, like for these two speakers. For these two speakers, they are the female speakers, and if you try to analyze their pitch values, you can see the distribution is different. You can see both of them are Gaussian, but if you look at that, the Gaussian parameters are very different. And here these two corresponds to two male speakers. If you look at the distribution again here also, it varies. So that way these plots indicating that there is a prosodic content or prosodic features which are specific to the speakers. And similarly here if you look at the dynamics of a prosody, that means here the two different speakers, they are uttering the days of the week, like a Monday, Tuesday, Wednesday, and so on. You can see the Monday to Sunday. So this is the top plot indicate when you are uttering the Monday, this is the pitch contour related to that. This is for Tuesday, this is for Wednesday, this is for Thursday, and so on. Likewise, this is for a particular speaker, this is for another speaker. So what I mean to say is that if the two different speakers, even though they utter the same sequence of words, if you observe the pitch contour, or if you observe their intonation patterns, they are very different. So based on that, you can able to like discriminate the speakers. So that's what speaker specific aspects of prosody. By exploiting these prosodic cues, one can able to differentiate, or you can able to like verify the speaker claim. and this is also similar to that. You can see that here the same fixed text was uttered by child, uttered by the two different male speakers and a female speaker. You can see the first one is that it is uttered by child, the same text utterance, and these two are like two different male speakers, and this is the female speaker and all. And if you look at the way the intonation patterns are varying, the dynamics of these things, the slopes and how they are varying, you can see they are varying. You can see here for a child the intonation patterns are lowering, you see, like, whereas in case of this particular male speaker, they are rising. First of there is a flat for some extent, and afterwards they are rising. And whereas here for this male speaker, it is almost like a flat, and for this female speaker you can see this is also lowering, like it is like a flat at the beginning, afterwards is lowering. So, that way what I mean to say is that for each speaker, when you are uttering the words, even though the words are uttered may be same across the speakers, but each speaker, the way he uttered, it has its own style or own way of uttering. So, that is known to be a speaker specific prosody, and that can be exploited for speaker recognition task. And again one more thing here is that, and again the prosodic features are very robust. So, for demonstrating that, here there are three plots here. The utterance that was uttered was don't carry an oily rag like that. This is the utterance, this is a text utterance uttered in the timid database, and here you can see these three utterances are corresponds to. So, first one is that the utterance that is taken from the timid database, and the second one is that the same utterance the same speaker has uttered, like from the noisy timid. It means the same timid utterances uttered in a noisy environment, and the other one is that C timid, it is the same timid utterance that was uttered, it was passed through the mobile phone or like a cellular environment and all. So, if you look at all these three, all three of them were uttered by the same speaker, but in the different environments. Even though they are uttered in the different environments, if you look at the way of intonation patterns, they are more or less same. They are of same. You can see that almost like you can say it is a beginning and then afterwards lowering and all. The same thing, almost similar patterns is observed even though in the different environments. So, that way the prosodic features, whatever the speaker specific prosodic features, so they are like robust in the sense that even though the speech is collected from different environments, they show the unique style or unique patterns irrespective of the background environments or the other environments. But if you look at, if you try to analyze the same thing, like here if you look at this particular plot is that there are two utterances uttered by the same speaker, but here we considered the features that are extracted from the vocal tract features, and here the two utterances are passed through, like they are from N timid and C timid, but both of them were uttered by same speaker. But here if you look at the vocal tract features or the spectral features, if you look at here, the black one corresponds to the spectral features from the utterance that is derived from the noisy timid. The same utterance, the same speaker when that is collected from the C timid. C timid is nothing but the timid database that is captured from the cellular environment. So, if you look at here, in both cases there is a lot of the variability that is present in the vocal tract characteristics, whereas in the prosodic characteristics whatever we have seen earlier, so they are almost like robust, even though it is captured from a clean C timid, that is a timid data that is captured from a cellular phone or like a noisy environment or clean case. All the cases the patterns are same, but here you can see there is a drastic variation between N timid and C timid, even though the same utterance spoken by same person, but the vocal tract features they are like highly variable. That means they basically depends upon the environment. So, the environment will play a crucial role in the case of vocal tract features. And so, then here how to extract the speaker specific features or prosodic features. So, here suppose this is the utterance and here the features are extracted at syllable level. So, therefore, first the syllable boundaries are identified using some signal processing technique, and afterwards you extract the intonation pattern or nothing but you derive the F0 contour, and then F0 contour is derived for the whole utterance, And now since you have the syllable boundaries, so this is one syllable and this is another syllable, this is another syllable. Likewise, here you can see there are 6 syllables were there. So within these boundaries, we will try to like parameterize this intonation pattern. So for parameterizing this intonation pattern with respect to each syllable, we use the technique known to be the tilt parameters. So here the tilt parameters like will try to like parameterize the any shape using these tilt parameters like amplitude tilt, duration tilt. You can see these are the amplitude like here the rise amplitude, this is the fall amplitude, this is the rise duration. That means the duration that is required to rise from this point to this point and fall from this point to this point, this is the fall duration, and this is the rise amplitude, this is the fall amplitude. So by using these rise and fall amplitudes and durations, so we can able to derive these parameters like amplitude tilt, duration tilt, and the change f naught and the other things, right. So these are known to be tilt parameters, and we can able to derive these tilt parameters for different scenarios. Either it may be simply falling or simply rising, a rise followed by falling, or a rise with longer duration. So all these cases you can able to parameterize with appropriate parameters. So these are the list of parameters. There are 7 parameters that can able to model the shape of the intonation contour within a syllable and all, right, within a syllable. That way you can able to capture the shape by using these 7 parameters, right, using 7 parameters like a mean value of f naught, peak value, then the change of f naught, distance of f naught, amplitude tilt, duration tilt, and so on. And then once these features are extracted, prosodic features, then by using these auto associative neural network, this is auto associative neural network, and here the auto associative means here the features whatever here you are giving, the same features also feeded at the output, and we will try to see that during the training we will try to see that the model whatever we are feeding here, we expect that the same thing has to be given as output. So in this process what happens is that during the intermediate or at middle layer, it is not to be compression layer, where these features will try to like represent the underlying relations in the features in a very compact way, Here you can say that here we are trying to, these are the features, we will try to expand that using the hidden layers. It is not only the one hidden layer, you can use the multiple hidden layers also, and with that it is it is expanded at the like kind of encoder here we are doing, and with that we are encoding the speech, and then afterwards we are performing the similar thing, whatever the layers are here, and whatever the layers, what are the number of units, the same symmetric structure will be used, and this is kind of encoding process, and this is a kind of a decoding process. So therefore the intermediate layer, the middle layer, the compressed layer, which compactly represent the features and all, and here you can able to see that by using these features, these compact features, you can able to discriminate the speakers and all. So for that actually whatever the features that are extracted from here, so that will be properly if you want to see that. So here you can see in the next plot, where here you can see by using the auto associative network of this structure, it contains the 5 layers, the 7 as the input, because the number of features that were considered were 7 different features, and then the hidden layer, the first hidden layer is it contains a more number of units. So therefore it is idea here is that the features will be projected to the high dimensional space, and afterwards it will be again projected to lower dimension space, and again we do the reverse process. So in that case the middle layer, which contains only the 3 units, it means that the 7 dimensional feature vector will be compactly represented by using 3 dimensional feature vector. So this is just for illustrating that using auto associative neural network we can represent the features very compact way, so that it contains the more generic information which can carries the discriminate information for the whatever the classes that are meant for discrimination purpose. So here by using this auto associative neural network we capture the features, and so these middle features will be taken out, and these middle features will be like projected. If you want to look at those features how they are, So, here you can see this the 3-dimensional feature whatever is there. So, that feature will be captured over here, right, and they are plotted here. If you look at here and suppose we plot the 2 speakers data, which is which will be like auto associating, this particular auto associating network will be used as the network for like capturing the compact features and all. And then if you take the, if you tap the features from a middle layer and then if you plot the 2 speakers speech, you can see here that the like these speakers are these features are very well discriminated. So, this plot is just to illustrate that the prosodic features will in turn can be used, can capture or can represent the speaker specific information, and with that if you properly use those features you can able to discriminate the features. And another advantage is that actually here the prosodic features are robust enough. It means that even though there is a variation in the recording environment and the recording transducers and the channels that are passing through, and even though there are variations in the at a speaker level, all of them can be properly represented or can be robust against to the speaker. So, therefore, you can able to, you can see here, you can here the prosodic features by plotting in this 3-dimensional representation, you can see a clear discrimination over here and all. It means all these belongs to one speaker, this belongs to another speaker. So, that way you can able to discriminate by using appropriately using the prosodic features. Okay, thank you.